All right, today we are diving into a theory that's trying to, well, basically rewrite everything we think we know about the universe. It's called Hydrodynamic Quantum Cosmology, HQC for short. And get this, it says the deepest secrets of the cosmos aren't hidden away in some weird extra dimensions or tangled up in string theory. Nope. The answer, it claims, is in something we see every single day: fluids.
Now, look, if you're going to come out with a new theory of everything, you have to start with a pretty bold claim, right? And this one does. It asks a simple, kind of terrifying question. Is modern physics just broken? According to the folks behind HQC, the answer is a big, resounding yes. And, the cracks are really starting to show.
I mean, for decades now, physicists have been banging their heads against the wall over some really deep problems. We've got measurements of how fast the universe is expanding that just don't agree with each other at all. We have this idea of a Big Bang, a starting point where all our laws of physics just completely fall apart. And then there's the big one, the most famous fight in all of science. General relativity and quantum mechanics are two masterpieces, and they absolutely refuse to get along. So, the fix HQC proposes is, well, it's not what you'd expect. There are no new undiscovered particles, no fancy extra dimensions. Instead, it just flips the whole problem on its head by asking a really simple question. What if the vacuum of space isn't actually empty? What if space-time itself is a real physical thing, like a fluid?
Okay, so before we dive into the solution, let's really take a closer look at these cracks, these puzzles in our picture of reality. First up is something called the Hubble Tension, and this one's a real head-scratcher. See, when we look way back at the early universe, we measure its expansion rate at about 67 kilometers per second per megaparsec. Don't worry, that's just a super huge unit of distance. But when we measure the universe closer to us, the late universe, we get a different number, 73. And here's the problem. Those two numbers should be the same, but they're not. And it's not a small error either. Their error bars don't even overlap. This is a genuine crisis in cosmology. And then, of course, there's the biggest crack of them all, the Great Civil War of physics. On one side, you've got Einstein's general relativity. It's the law of the big stuff, planets, galaxies. It's all smooth, continuous, predictable, beautiful. On the other side, you have quantum mechanics, the law of the tiny. And it's a chaotic, jumpy, probabilistic mess. They are two completely different ways of describing reality, and they just don't work together at all.
So how does HQC even begin to fix this? Well, it suggests we've been thinking about space-time all wrong. We tend to think of it as just the empty stage where the play of the universe happens. HQC says, no. Space-time is the play. It's the actor itself.
The theory says space-time isn't just any fluid, it's a superfluid. Now, this is a real thing. It's a bizarre state of matter with absolutely zero viscosity. That means it can flow forever without any friction, without losing any energy. And here's where it gets really wild. In this model, the universe didn't start out hot, like in the Big Bang. It started at absolute zero. What we call space is just what happened when this ultra-cold primordial fluid went through a massive change, a phase transition.
Okay, but wait a second. If a superfluid has zero viscosity, zero friction, how in the world do you get gravity? Gravity is all about things pulling on each other. Well, this is where the theory gets really clever. It introduces a twist, a two-component viscosity. Think of it like this. There is a radial viscosity, which is a resistance to being stretched or compressed. That's what we feel as gravity. But the transverse viscosity, the resistance to things moving sideways, is still practically zero. And that's why planets can just keep orbiting for billions of years without ever slowing down.
All right, so we've got our fluid space-time model. A pretty wild idea, but does it actually solve anything? Does it fix those cracks we talked about? Well, this is where things get really, really cool.
Let's start with maybe the most fundamental question you can ask. What is stuff? I mean, really, what is an electron? What's a quark? What are they made of?
The answer HQC gives is, well, it's just beautiful. Particles aren't tiny little specks of something floating in space. Particles are space. They're tiny, stable, swirling vortexes, like little knots in the superfluid of space-time itself. The best way to picture it is to think of a smoke ring. It's not a thing, it's just a stable, swirling pattern in the air that can travel across a room. In this theory, matter is just that, a persistent pattern in the fabric of reality. And what's amazing is that this simple idea seems to explain the three generations of matter perfectly. You've got your generation 1 particles, like electrons and up quarks. These are the simple, stable knots, like a basic trefoil. Then you have generation 2 particles, like the muon. They're more complex knots, and they're less stable. They fall apart. And finally, generation 3, like the top quark, are super complex, super intricate knots. They're incredibly unstable. And their huge mass, it's just a measure of how much length of the spacetime fluid you need to tie such a complicated knot. It just fits.
Okay, next big puzzle. If the universe started out at absolute zero, what happened to the Big Bang? Well, HQC flips the story completely upside down. It says the Big Bang wasn't a Big Bang at all. It was a big freeze. It wasn't a hot, dense explosion. It was a phase transition. Imagine you have supercooled water. Water that's below freezing but still liquid. If you tap it, it instantly crystallizes into ice. HQC says that's what happened. The universe started as a kind of high-energy liquid, and then it rapidly froze into the structured spacetime we live in now, releasing a ton of energy as it did. And the best part? The singularity, that point where all our physics just dies, it's gone. It never happened. It's just replaced by a physical process we actually understand.
And that brings us to the Holy Grail, the biggest claim of HQC and really the dream of every physicist for the last century: unifying general relativity and quantum mechanics.
The core idea here is just so simple and powerful. What if GR and QM aren't two different warring theories? What if they're just two different descriptions of the same fluid behaving in different ways? Think about water flowing from a tap. At first, it can be a smooth, glassy, predictable stream. That's laminar flow. That's general relativity. But if you turn the tap up, it becomes a chaotic, churning, unpredictable mess. That's turbulent flow. And that, HQC says, is quantum mechanics.
So what's the switch? What flips a fluid from smooth and predictable to chaotic and turbulent? In fluid dynamics, it all comes down to a single, very famous number. A number that acts as the bridge between these two completely different worlds.
And that number is called the Reynolds number. It's basically a simple ratio that compares how much a fluid wants to keep going versus how sticky it is. It tells you with incredible accuracy whether the flow is going to be orderly or chaotic. And what HQC does is take this classic idea from building pipes and designing airplanes, and this leads to what might be the single most powerful statement in the whole theory. You know, Planck's constant, that bedrock fundamental number of all quantum mechanics? HQC says it's not just some abstract constant. It's a real physical property of the space-time fluid. It is the kinematic viscosity of the vacuum, its resistance to flow. Think about what that means. It means that all the weirdness and uncertainty of the quantum world, it's just turbulence. It's the inherent chaotic churning of space-time at the tiniest scales.
Okay, let's go one step further. We're now entering the most audacious, the most speculative, but maybe the most beautiful part of this whole idea. It suggests that the universe is, deep down, way simpler than we ever thought.
Okay, take a look at this. The fine structure constant. It's a crucial number that basically sets the strength of electromagnetism. Our best measurement for it is 137.035999. Now, HQC proposes that this number isn't just some random value that happens to be what it is. It says it comes directly from pure geometry, from the relationship between spheres and circles. And when you calculate it using their formula, you get 137.0363. That is incredibly close. The error is a tiny fraction of a percent.
And this points to the ultimate dream of the theory. Right now, our standard model of physics needs something like 26 different constants, numbers we just have to measure and plug into the equations by hand. We have no idea where they come from. HQC claims the real number of fundamental constants is 0. That's right, 0. In this universe, every single one of those constants should just emerge naturally from the geometry of spacetime, in the same way the number pi emerges from the geometry of a circle.
And that leaves us with one last, truly mind-bending thought to chew on. If all the fundamental rules and constants of our universe are really just geometric relationships, it suggests something pretty profound. Maybe the universe isn't just something that math is really good at describing. Maybe the universe at its deepest, most fundamental level is math.